Welcome to AI Frontiers, where we explore the cutting edge of artificial intelligence research. Today we're diving into the latest developments in computer vision, a field that continues to transform how machines perceive and understand the visual world around us. Computer vision represents one of the most dynamic and rapidly evolving branches of artificial intelligence, with applications spanning from autonomous vehicles and medical diagnostics to augmented reality and industrial automation. The papers we'll be examining today showcase the remarkable diversity and innovation that characterizes this field, offering insights into where computer vision technology is headed in the coming years. Join us as we explore key research trends and breakthroughs that are shaping the future of how machines see and interpret the world. Computer vision is an interdisciplinary field that combines machine learning, pattern recognition, and image processing to enable computers to extract meaningful information from visual inputs. At its core, it aims to replicate and extend human visual capabilities through computational methods. The significance of computer vision has grown exponentially in recent years, driven by advances in deep learning, increased computational power, and the proliferation of visual data across virtually every sector of society. What makes computer vision particularly fascinating is its broad applicability. The same fundamental techniques can be adapted to recognize faces in social media photos, detect cancerous cells in medical images, guide autonomous vehicles through complex environments, or enable augmented reality experiences. This versatility has made computer vision a critical component of many technological innovations that are reshaping our world. As researchers continue to push the boundaries of what's possible, we're witnessing remarkable advancements in how machines interpret the visual world, addressing persistent challenges such as efficiency, accuracy, interpretability, and adaptability across different domains. The first major theme emerging in current computer vision research is multimodal integration, particularly the fusion of visual and textual information. This approach has gained significant traction as researchers recognize that combining different types of data can lead to more robust and comprehensive understanding. Vision language models represent a particularly active area of research, with systems designed to process and reason about both images and text in an integrated manner. One influential study by Guo and colleagues introduced SEED 1.5-VL, a vision language foundation model designed for general-purpose multimodal understanding and reasoning. Despite its relatively compact architecture, this model delivers impressive performance across a wide spectrum of benchmarks and excels in agent-centric tasks such as graphical user interface control and gameplay. In another example, Nguyen Quoc and colleagues proposed SCOLD, a context-aware vision language foundation model tailored specifically for agricultural tasks, particularly leaf disease identification. Developed using a diverse corpus of plant leaf images and corresponding symptom descriptions, this model leverages contextual soft targets to improve generalization on fine-grained classification tasks. Connell and colleagues addressed the critical issue of hallucination in vision language models for medical image analysis by curating a multimodal image-text gastrointestinal dataset with expert-reviewed annotations. Their approach focuses on detecting and correcting hallucinations rather than simply fine-tuning for descriptive report generation, addressing a key challenge in applying AI to healthcare contexts. The second major theme in current computer vision research is the development of more efficient deployment strategies for deep learning models. As computer vision systems grow more sophisticated, researchers are increasingly focused on making these models accessible by reducing their computational demands. This is particularly important for deployment in resource-constrained environments, such as edge devices or Internet of Things applications. Stropini and colleagues investigated how to perform visual anomaly detection effectively within Internet of Things environments by leveraging compact and efficient processing strategies. Their work demonstrates that significant compression can be achieved with minimal loss in anomaly detection performance compared to uncompressed data, making sophisticated visual analysis feasible even on devices with limited computational resources. Similarly, Borno and colleagues introduced KDC-Diff, a streamlined diffusion framework that reduces model complexity while maintaining image quality. Their approach features a U-net architecture with nearly half the parameters of the original model, making high-quality image generation more accessible in computationally constrained settings. Chen and colleagues addressed the challenge of processing high-resolution images in multimodal large language models by introducing the chain of region of interest method. This approach selectively focuses on the most informative regions of high-resolution images rather than processing the entire image at full resolution, significantly reducing computational requirements while maintaining or even improving performance on visual understanding tasks. These efficiency-focused innovations are proving that architectural improvements can be more important than simply increasing the raw parameter count of models. The third prominent theme in current computer vision research is the advancement of diffusion models for image generation and editing. Diffusion models have emerged as a powerful paradigm for creating and manipulating visual content, with researchers exploring various enhancements to improve their flexibility, efficiency, and output quality. Liu and colleagues proposed SAMSR, a semantic-guided diffusion framework for single-step image super-resolution that incorporates segmentation masks to preserve spatial and semantic features, particularly in complex regions of images. By prioritizing semantically rich regions during the diffusion process, this approach achieves superior results in a single step, making high-quality super-resolution more practical for real-time applications. Shaw and colleagues presented DAPE, a dual-stage parameter-efficient fine-tuning framework for consistent video editing with diffusion models. Their approach addresses limitations in both training-required and training-free methods by offering a cost-effective solution that enhances temporal consistency and visual quality in generated videos. This work demonstrates how diffusion models can be extended beyond static images to handle the additional complexity of temporal coherence in video content. Li and colleagues introduced CMD, a controllable multiview diffusion model that enables flexible local editing of 3D models. This approach allows for the generation of 3D models part by part and permits local editing according to revisions in the input image without affecting other components. By formulating 3D generation as a conditional multiview diffusion model, CMD represents a significant advancement in how we interact with and modify 3D content. The fourth theme of growing importance is the development of explainable AI and concept-based explanations for computer vision systems. As AI systems become more complex and are deployed in increasingly critical applications, understanding their decision-making processes grows increasingly important. Several research efforts are addressing this challenge through concept-based explanations and interpretable frameworks. Varshni and colleagues introduced concept directions via latent clustering, which extracts global, class-specific concept directions by clustering latent difference vectors derived from factual and diffusion-generated counterfactual image pairs. When validated on a real-world skin lesion dataset, the extracted concept directions align with clinically recognized dermoscopic features and, in some cases, reveal dataset-specific biases or unknown biomarkers. This demonstrates that their approach is not only interpretable and scalable but also capable of uncovering meaningful patterns that might otherwise remain hidden. Liu and colleagues proposed a differentiable non-maximum suppression framework for fabric defect detection that achieves superior localization precision through end-to-end optimization. Their approach specifically targets irregular morphologies and ambiguous boundaries by integrating proposal quality, feature similarity, and spatial relationships, making the detection process more interpretable and effective for industrial quality control applications. Yang and colleagues developed XMed-GPT, a multimodal explainable medical AI assistant that not only produces accurate diagnostic outputs but also grounds referenced anatomical sites within medical images. This work addresses a fundamental challenge in medical AI by providing transparent, explainable assistance that clinicians can trust, potentially transforming how AI is integrated into clinical workflows. Let's examine some of the most groundbreaking findings that have emerged from recent computer vision research. These key results represent significant advances that could shape the future direction of the field. One of the most significant findings comes from Guo and colleagues' work on SEED 1.5-VL, a vision language foundation model that achieves state-of-the-art performance on 38 out of 60 public benchmarks despite having a relatively compact architecture. This result is particularly significant as it demonstrates that carefully designed smaller models can compete with much larger ones, potentially democratizing access to powerful vision language capabilities. By showing that a compact model can achieve such impressive results, SEED 1.5-VL challenges the prevailing trend toward ever larger models and suggests that architectural innovations and training methodologies may be more important than raw parameter count. Lee and colleagues' work on CMD, a controllable multiview diffusion model, represents a significant advancement in 3D generation and editing by enabling flexible local editing of each component of a 3D model without affecting other parts. This approach fundamentally changes how we interact with 3D generation models, making it more accessible and intuitive for users without specialized expertise. Connell and colleagues make a significant contribution to medical image analysis with their hallucination-aware approach to vision language models, establishing a new paradigm for developing reliable vision language models in medical contexts. Yang and colleagues' XMed-GPT achieved a remarkable 26.9% improvement in cancer prediction over previous leading models, demonstrating the potential of explainable AI to transform healthcare applications. Several methodological approaches appear consistently across current computer vision research, representing the state of the art in the field. Diffusion models have emerged as a dominant framework for generative tasks, with researchers incorporating semantic guidance to improve quality while reducing computational requirements. These models work by gradually adding noise to data and then learning to reverse this process, generating new samples by iteratively denoising random noise. The strengths of diffusion models include their ability to generate high-quality, diverse outputs and their flexibility in incorporating conditional information. Multimodal foundation models that combine vision and language capabilities through careful architecture design are another prominent approach. These models typically feature separate encoders for different modalities, followed by fusion mechanisms that allow for integrated reasoning across modalities. Contrastive learning has proven effective for similarity assessment in applications like ballot verification, as demonstrated in Zhao and colleagues' mark match system for detecting whether ballot marks were filled by the same hand. Domain-specific fine-tuning addresses specialized needs in medicine, agriculture, and other fields by adapting general models to particular contexts. Finally, efficient architectures such as U-net variants and mixture of experts (MO) models are being developed to balance performance with computational constraints, enabling deployment in a wider range of environments. Let's take a closer look at SEED 1.5-VL, a compact yet powerful vision language model developed by Guo and colleagues. This model achieves state-of-the-art performance on 38 out of 60 public benchmarks despite having a relatively compact architecture compared to other leading models. SEED 1.5-VL combines a 532 million parameter vision encoder with a mixture of experts language model utilizing 20 billion active parameters. What makes this work particularly noteworthy is that it outperforms much larger models, including OpenAI Kua and Claude 3.7, in agent-centric tasks such as graphical user interface control and gameplay. This research was selected for discussion because it challenges prevailing assumptions about model scaling requirements in the field of computer vision. By demonstrating that a carefully designed architecture with thoughtful training methodologies can achieve superior results without simply scaling up parameters, SEED 1.5-VL points to a future where powerful vision language capabilities might be more accessible to researchers and developers with limited computational resources. This work suggests that the field may benefit from focusing on architectural innovations and training efficiency rather than continuing the trend toward ever larger models that require massive computational resources. CMD, or Controllable Multiview Diffusion, developed by Lee and colleagues, represents a transformative approach to 3D model generation and editing. Unlike previous approaches that generate entire 3D models from an input image or text prompt, CMD enables component-wise generation and editing of 3D models without affecting other parts. This is achieved by formulating 3D generation as a conditional multiview diffusion model that takes existing or known parts as conditions and generates only the edited or added components. What makes CMD particularly significant is that users can modify specific parts of a 3D model by editing just one rendered image, representing a paradigm shift in 3D content creation accessibility. This approach fundamentally changes how we interact with 3D generation models, improving generation quality while enabling efficient and flexible local editing. Instead of treating 3D generation as a monolithic task, CMD decomposes it into multiple components, making the process more intuitive and accessible for users without specialized expertise. This research was selected for discussion because it could transform workflows in fields such as product design, architecture, and entertainment, where 3D content creation is essential but often requires specialized skills. By making 3D editing more accessible and intuitive, CMD points to a future where complex 3D content creation becomes available to a much wider range of users. XMed-GPT, developed by Yang and colleagues, represents a significant advancement in creating trustworthy medical AI systems. This multimodal explainable medical AI assistant not only produces accurate diagnostic outputs but also grounds referenced anatomical sites within medical images, bridging critical gaps in interpretability. The model achieves an intersection over union of 0.703 across 141 anatomical regions, demonstrating strong alignment between visual rationales and clinical outcomes. For uncertainty estimation, it attains an area under the curve of 0.862 on visual question answering and 0.764 on radiology report generation. Most impressively, in survival and recurrence prediction for lung and glioma cancers, XMed-GPT surpasses prior leading models by 26.9% and outperforms GPT-4o by 25.0%. This research was selected for discussion because it addresses one of the most significant barriers to AI adoption in healthcare: the lack of transparency and explainability in AI decision-making. By providing transparent, explainable assistance that clinicians can trust, XMed-GPT could accelerate the adoption of AI tools in healthcare settings where trust and interpretability are essential. The ability to ground diagnoses in specific regions of medical images allows clinicians to verify the AI's reasoning, potentially increasing confidence in AI-assisted diagnoses and leading to better patient outcomes. This work demonstrates how explainable AI approaches can be successfully applied in high-stakes domains where understanding the basis for AI-generated insights is as important as the insights themselves. Looking ahead, several clear directions are emerging for the future of computer vision research. Multimodal foundation models will continue to integrate vision with language, audio, and other modalities, creating more comprehensive AI systems capable of understanding the world in ways that more closely resemble human perception. These models will likely become increasingly specialized for particular domains while maintaining general capabilities across a wide range of tasks. Efficiency-focused research will remain a priority as researchers seek to democratize access to powerful models on everyday devices. This includes developing more parameter-efficient architectures, exploring quantization and pruning techniques, and creating specialized hardware accelerators for computer vision tasks. Explainable AI approaches will become essential not only for scientific understanding but also for regulatory compliance and user trust. As computer vision systems are deployed in increasingly critical applications such as healthcare, autonomous vehicles, and security, the ability to understand and verify their decision-making processes will be paramount. Domain-specific adaptations of general computer vision techniques will proliferate in healthcare, agriculture, and specialized industries, addressing the unique challenges and requirements of these fields. Finally, 3D and video generation capabilities will continue to mature with improved temporal consistency and controllability, opening new possibilities for content creation and simulation across various domains. This presentation was created through a synthesis of recent research papers in computer vision, with content synthesized using Anthropic Claude 3-7 Sonnet 20250219. The text-to-speech narration you're hearing was generated using Google TTS technology, while visual elements were created with Grok image generation. All synthesized content has been reviewed by a human expert for accuracy and coherence to ensure that the information presented faithfully represents the current state of computer vision research. While thorough review was conducted, some oversights may exist in the final presentation. All references to original research papers have been preserved to allow listeners to explore topics of interest in greater depth. This approach to content creation represents an example of how AI tools can be used to make complex technical information more accessible while maintaining scientific accuracy and intellectual rigor. The synthesis process involved analyzing patterns across multiple research papers to identify common themes, methodological approaches, and significant findings, then organizing this information into a coherent narrative structure. Subscribe to AI Frontiers for weekly research syntheses on cutting-edge AI developments across various domains. Join our community of AI researchers, practitioners, and enthusiasts to stay informed about the latest breakthroughs and their implications. If you have specific research topics or fields you'd like us to cover in future presentations, please let us know through our website or social media channels. Follow us on social media for additional insights and discussions that extend beyond our podcast content. Visit ifrontiers.com for full research references and supplementary materials related to this and other episodes. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.